Okay, as it is 1 minute past, we will make a start here. So hello everyone, welcome again to this week's Topos Institute Colloquium. I'm really pleased to say we've got Andrew Blumberg here today speaking to us about, sorry, I actually can't see your slide title. I'm going to assume persistent homology and topological data analysis and things related to this. Sorry, I should have prepared better for that.
No.
And Andrew said, so feel free to interrupt. You can unmute yourselves. So, you know, if there's something you'd like clarified, feel free to either unmute yourself or ask in the chat, either publicly or straight to me. And we'll, you know, I can ask the questions or you can ask them at the end, whatever. It's kind of a semi-informal in this sense. So, Andrew, whenever you would like to talk about what you're going to talk about, please do.
Thank you. Yes, thank you for inviting me to do this. It seems like it will be fun. So yeah, what I want to talk about is trying to understand persistent homology and topological data analysis from the perspective of abstract homotopy theory. And in some sense from a categorical perspective. And so I will try to unpack what that means. I don't want to assume you know anything about topological data analysis, so I want to go through that to begin. But the motivating question, just to say, for this whole thing is, what sort of thing is persistent homology? And maybe I say the punchline now, and then for people who know it and come back to explain. When we think about homology theories, traditionally, one of the big insights of modern algebraic topology, arguably right at the beginning, is the characterization of homology theories as functors in terms of the Eilenberg-Steenrod axioms, right? And before this, there was a lot of work to show that different kinds of homology theories led to the same output. If you used models of spaces from simplicial complexes, or you used models of spaces from, differential forms, models of the chains. And the axiomatic characterization says that, you know, if you satisfy these axioms, then you are isomorphic to regular homology. And a lot of what the talk is about is trying to understand a picture like that. And we don't at all, I think, but trying to understand a picture like that in the context of topological data analysis. So let me start by trying to say something about what is persistent. Erase that. What is persistent homology? And this is, you know, topological data analysis can mean many things, but certainly one very strong thread of work surrounds this idea of taking a sort of homology of a filtered complex. And that's what I want to talk about today. And so there's a pipeline, which is that you start with your data presented as some kind of finite metric space. And that has no intrinsic topology, or it's discrete. But from that, we are going to produce a filtered simplicial complex. And where a simplicial complex is a combinatorial model of a space, and the filtration arises typically from letting the feature scale of the assumed feature scale of the data vary. From this filtered simplicial complex, by applying something like homology, we obtain a filtered vector space. Happening. And from the filtered vector space, we finally obtain an output called a barcode. So I want to walk through a very high-level review of this procedure to situate what we're studying. So, okay, so we have this data presented as a finite metric space, and an example to keep in mind. This is, from the perspective of data analysis, this is a very misleading example, but for a mathematician, this is the example everyone likes, which is, you know, imagine that your finite metric space is obtained by sampling from a compact Riemannian manifold, probably embedded in Euclidean space, and you sampled using the volume form. So you uniformly sampled from a compact Riemannian manifold, and then you gave those points the subspace metric, considered as things embedded in Rn. So the question now is, can we assign, so we have a manifold, we sampled finitely many points from it, can we assign to that a simplicial complex that recovers something about the homotopy type of the underlying manifold? And the answer is yes, under the right conditions. And so what are we going to do? So we're going to assign a simplicial complex to X. And a simplicial complex, remember, this is a combinatorial model of a space where you build spaces out of gluing instructions for standard simplices. The standard simplices are convex hulls of the unit vectors in Rn. And these look like, a point and a line. Maybe I sort of draw the first couple, a point and an interval, and something that looks like a triangle. And then this part I'm maybe less able to draw so nicely, but a pyramid, and then sort of higher dimensional pyramids. And the point about these things is that you can glue them together along their faces. Right? This thing has 3 faces, and each face is an interval. And similarly, this thing has 4 faces, and each face is a triangle. And so the idea is to think about modeling spaces by gluing these together. And this turns out to be a rich thing to do, but it's also algorithmically tractable because you require a count for how many of each of these things you have, and you require some compatibility and gluing information about how they fit together. So in the case of what we might do for a finite metric space, we can build, one kind of thing we can do is build something called the Vietoris-Rips complex. How does this work? Well, we fix epsilon greater than 0. And that's our scale parameter. And the way we define the complex, it has 0 simplices, which are just given by the points of X. So we start with the points. And now we connect those points by a line. So we make a graph from this where 2 points X, Y are connected if the distance between them is less than epsilon. If it's greater than epsilon, they're not connected. If it's less than epsilon, they are. And now we add in a triangle, or in general, an n-dimensional simplex, if every pair of points on that, at the vertices of that simplex have distance less than epsilon. So, what does an example of this look like? Maybe we have something like this, right? Our underlying, or I have an example down here. So our examples, if we sampled, and maybe I should draw, if our underlying manifold was a circle, and we finitely sampled these black points from it, then depending on what we fit epsilon to be, different things could happen. When epsilon is equal to 0, then nothing happens. No one is connected, and this is what tends to get referred to as dust. And if epsilon is very small relative to the minimum distance between these points, you see nothing. But at some point, epsilon you can pick an epsilon that is larger than, if you pick an epsilon that is larger than the minimum distance, and you start connecting things. And so maybe if we pick epsilon to be, let's choose a different color, if epsilon maybe is on this scale, then we start connecting these points like so. And this hasn't recovered a circle yet, but we now are starting to see signs of geometry arising out of this simplicial complex. And if you make epsilon bigger, the idea is that as you do that, eventually you're going to connect all the way around the circle. Now, of course, in a real example, you probably really didn't sample from the circle per se, but from some sort of little annulus around it. Maybe there was noise in your ambient space. And when that happens, what you really get is you get these little cross connections. And maybe you fill in some of these triangles. So you start to fatten out some combinatorial object that starts to look like the geometry of this circle. And that's sort of the stuff that happens in here. If you choose epsilon to be enormous, so if epsilon is bigger than the width of the slide, then every point is connected to every other point, and moreover, every higher triangle is present. And what you have is a giant contractible object that has no non-trivial topological features again. In some sense, one way to hear what this looks like is you fill in the disk. You connect across and you filled in the disk. And now this maybe is a regime we might call heat death. But somewhere in the middle, if you knew how to pick epsilon just right, and you sampled densely, then you would hope and you can prove that you, in fact, can recover at least the homotopy type of the circle from this. Now, I should say as an aside, I will focus on this process as our motivating example of a simplicial complex. There are many, of course, many ways you could try to play a game like this and assign a simplicial complex to a finite metric space. Another very, sort of very familiar one, maybe depending on what part of the world you grew up in, is the check complex. And here, so in the case of the Vietoris-Rips complex, everything is determined by that graph of the 0 and the 1 simplices. Once you have that graph, you know everything else because an n simplex is there if all the edges in the graph between its points are there. And so it's the simplicial complex that's determined by this one, that's sort of freely determined by this one skeleton. But you could do something more sophisticated where if you had a collection of n points, and especially if you were embedded in Euclidean space, you could blow up balls around of radius epsilon. And you could ask, is there a point in the intersection of all of those balls? And if there is, then you could add the k-dimensional simplex corresponding to that. And that's called the check complex. The Vietoris-Rips complex is easier to compute and easier to talk about. The check complex, one expects, is maybe slightly more faithful to the topology. But, that's not, or maybe all I want to do is mention that there are these choices and not worry about it. So the key observation that leads to topological data analysis. So the problem with the procedure that I just gave is you have to know what epsilon is. And that's wrong. It's wrong to want that. It's wrong to want that because in principle, you can't know. We probably know some range. If you know your data, you know some range in which the correct feature scale lives, but you can't know what it is precisely. And it's sensitive to the sampling and all these, and the noise and all these things you probably can't measure. And two, it's wrong because it isn't true necessarily that the feature scale is constant across what you're studying. Imagine you're studying some kind of singular surface. I folded a piece of paper. The feature scale around that fold ought to be different than the feature scale way far away on some flat part of the paper. How many points you need are different to see that. And that kind of example is ubiquitous. So it's just not right to think about having a single epsilon. And so, this is, I mean, people have known this idea that you want multi-scale invariants of things for a very long time. But the really interesting idea that is behind the idea of persistent homology is that what you observe is that this construction of the Vietoris-Rips complex is a functor. It's a functor from R. I mean, this is an area where I'd like using, it's nice to use the categorical language, but I'm saying something very simple. I'm taking all the order poset R regarding its category. So all I'm really saying is that if epsilon prime is greater than epsilon, then the Vietoris-Rips complex for epsilon sits inside of the Vietoris-Rips complex for epsilon prime. And why is this? Because as you increase that scale parameter, you are monotonically adding simplices. Never delete anybody, but sometimes you add new ones. And so there's this. So now, if I have a metric space, rather than choosing an epsilon, I can think about a filtered simplicial complex, which is, this diagram of complexes. And in principle, we're talking about a diagram indexed on R, and that maybe is frightening. But really, in any actual scenario, you had finitely many points. And so there are only finitely many values, real numbers for which the topology can change, and they're isolated. And so, because you could worry about weird stuff as you approach limit points, if you just, what would happen to the topology. But in the kinds of examples that one cares about, that doesn't happen. You have some sort of tameness condition, which says that things are comparatively nice. So now, and in fact, it's fine to think of this as being indexed on the natural numbers, where those are just indices for each of the real values at which the topology changes, at which the complex changes. So now to this, we can apply simplicial homology. So for any simplicial complex, you can compute homology. And what this does, this is a functor. We're going to take simplicial homology with coefficients, let's say, in a finite field, FP. And this is a functor from complexes to vector spaces. So I'm assigning to this thing a vector space. And roughly speaking, if you are not familiar with this, roughly speaking, what this is doing is counting the number of there's one of these for each natural number. I should have decorated that as HN. And HN of FP is roughly a count of the n-dimensional holes in the thing you're looking at, or the rank rather of that vector space is a count. So for instance, if we look at this and at this, what to say? So the rank of this is 1, and so the homology maybe is FP, at least at H1. So there's one-dimensional hole, so to speak. That circle goes around. Here there are 2. This is a figure 8 of some sort, and so you might expect to see, and you do get FP plus FP. And now one thing that you can wonder about and is maybe worth noting is that, of course, one simplified thing you might do is just keep track of the number, of the count. But it turns out to be very powerful to keep track of the vector spaces, because the vector spaces let us talk about, because of functoriality, basically, the vector spaces let us think about the relationship as epsilon changes between these things. Namely, if I just keep track of, this is 1 and this is 2, there's no, 1 is less than 2. They're different, but that's basically all I can say. If I keep track of the vector spaces, then I can distinguish the situation where this maps to this from the situation where this maps to this. Right? Those are different homomorphisms, and which is visible if you keep track of these vector spaces. So it's worth having this richer invariant. And so now, where are we? So now we have this collection of filtered vector spaces. And this is so this is a diagram of vector spaces we got from our finite metric space. And now you can do something else. So that's fine. Like that's having a diagram of vector spaces, or a diagram, of abelian groups or modules. That's a fine algebraic gadget. But there's a further really interesting insight, which is that for a given element, for what's called a homology class at a fixed feature scale. So if I fix epsilon j here and look at that's some vector space, and if I take a generator, I take some class in it. If I look back at this picture, I can ask that class, if I move it forward in time, or in feature scale, so to speak, if I look at the homomorphisms that take it forward, eventually it goes to 0. Right? We know that everything goes to 0 because of this heat death phenomenon I described, but eventually that class goes to 0, and you can ask, when does it go to 0?
Actually, Andrew, can I interrupt with a question?
Yeah.
So in the previous up about an inch and a half, there is, if you look at the basis here as sets, like there are 2 functions from the 1-element set to the 2-element set. So you really could draw those 2 arrows if you just map to sets instead of vector spaces.
That's right.
Is there a case where, does this functor factor through sets?
No, because you can have interesting, you can wind around those circles.
And that actually happens when you do this inclusion? That can actually occur?
Yeah.
Oh, wow. Okay.
I mean, not if it's an inclusion, but that map could be a winding map.
Are these vector spaces come to us through the Viator-Rips functor?
Yes.
Does that functor factor through sets?
No.
Okay.
Yeah, you really, I mean, you could project it to sets, but it doesn't factor through sets.
That was a question. Okay, thanks a lot.
Yeah. So right. So you can ask about when this class dies, and you can also ask, if you go backwards in time, when does this class first appear? You can look at things that hit it, and you can ask, when is there nothing before it that hits that class? And this, I guess you can ask about the image of the maps forward, and you can ask about the image of the maps backwards, and that gives you some kind of lifetime for that class. And how do you think about that? Geometrically, I mean, let's go back to maybe I just draw again. If we think about our example of the circle, when epsilon is really small, you don't see, at some point, there's going to be a homology class, the generator of that vector space that represents going all the way around the circle. But if the points aren't connected, it's not there. So when epsilon is small, there's no such thing. And so at some value of epsilon, suddenly that thing winks into existence. And then it lasts for a while, but eventually, you end up you cross-cut the circle if epsilon is big enough, and that fills in the disk, and then that kills that class because there's no longer a hole. You filled it in. And so there's a time, so to speak, or there's a feature scale period for which that thing is there. And before that, it's not, and after that, it's not. And you can summarize. It turns out that you can summarize all of the information in this filtered collection of vector spaces in terms of what's called a barcode, which is a picture that looks like this. And each of those lines is a generator. And the y-axis is meaningless. The vertical axis is meaningless. You're just ordering different things. And the horizontal axis is the feature scale. So this is the picture. There's one picture for each dimension of homology. This is down here is the epsilon axis. And so as epsilon grows, suddenly some things appear, and then eventually they disappear, and they disappear at different times. And, so for instance, what does a picture of this maybe look like if my underlying thing was a circle that looked like this, and I sampled at a uniform density, then this circle here would fill in much sooner than this circle here. And so you expect to see sort of different lifetimes of the bars representing this thing and this thing. Now, the fact that you can do this, so one thing to say is that the way, and I haven't said enough to justify this, so let me make an assertion. An assertion about homology, which is that you can compute the advantage of using these combinatorial models of spaces in terms of simplicial complexes is that you can compute homology as a linear algebra problem. And you have these vector spaces, and you're going to have it comes from looking at the kernel and image of some matrix, which represents the geometric operation of taking the boundary of something. And so it is not 100% obvious that you can do the linear algebra in a nice way so that you choose bases that make sense of this issue of computing lifetimes. Right? If you think about how to do that, there's it's asking you to choose consistent choices of bases as epsilon varies, and it's not immediately obvious you can do that, but you can. And again, if you know your commutative algebra, that's a consequence of something called the Artin-Rees lemma. Artin-Rees construction, the proof of the Artin-Rees lemma, I guess. If you don't know your commutative algebra, then take my word for it. It's a problem that can be easily solved, it turns out. And I should say that I haven't said any names. I mean, this idea of persistence was invented by Edelsbrunner and Lesher and Harrer, and this perspective on it in terms of the Artin-Rees lemma was really figured out by Afra Zamarodian and Gunnar Carlson, and and then of course widely propagated. Okay, so the thing that's really interesting, one of the things that's really interesting, so we turn a filtered vector space into a barcode. That's the name for this kind of picture. And the barcode, that's just a bunch of intervals, right? It's like pairs of points, but it's a multi-set in R2 basically. It's where you restrict, you want the right hand end to be bigger than the left hand end. But this is where things become different. So far what we've done is, okay, if you knew what homology was, well, now you know what homology, just some sort of filtration on homology, and that's, it feels qualitatively similar. But the different thing that happens now is that the set of barcodes, once we think of these as these intervals, this is a metric space. Homology, if you think about vector spaces, there's not really you can imagine sort of trivial metrics, but there's not a great metric on the collection of vector spaces. And why did you want a metric? Well, you want to know we want to have an answer to the following kind of question, motivated by our interest in data. Right? This isn't just mathematics, right? This is motivated by, I actually had these points I got somewhere, and I want to do something with them to find out the shape of whatever process generated them. And in that setting, you need to ask questions like, if I perturb those points just a little bit, do I perturb the topological output a little bit? And in the case of homology at a fixed feature scale, that question doesn't have such a great answer, because in part because the ways in which you can change homology are very coarse. You can suddenly add a new generator, change the dimension. But this is a metric space, and the metric space is, there are various choices, but notably something called the bottleneck metric and the Wasserstein metric. But all of these rely on, I guess I didn't draw a picture of it. I should do that. The idea is this: if I have this barcode, and now I have, let's say, this barcode, what am I going to do? I'm going to think about a matching between the bars. I'm going to match up the bars, and I'm going to match maybe this long bar. I'm going to match with this bar, and I don't know, I'll match this short bar with this bar, and I'll leave this other bar is going to be unmatched. And then I have a penalty, and the penalty is the excess in the matching. Right, I look at how well those bars overlap each other, and they're not going to overlap perfectly. There's some excess, and I assign that to a penalty term. And I take the best matching, the one that minimizes that excess. And and this is a metric. As it's easy to check this is a metric. It's since we can compute matchings, it's something you can try to compute. And so now we have the output lands in a metric space, and interestingly, the input is also can be endowed with a very nice metric. So the category of finite metric spaces, or at least let's say the set of finite metric spaces for the time being, also has a metric called the Gromov-Hausdorff metric. And as the name suggests, this was invented by Gromov as a generalization of the Hausdorff metric. And so let me remind you, the Hausdorff metric is an interesting metric on subsets of a fixed space and of a fixed metric space. And basically the metric is this: you take the smallest epsilon such that A sits inside an epsilon fattening of B, and B sits inside an epsilon fattening of A. And by epsilon fattening, what I mean is, you take all the points that are within epsilon of that thing. So you're sort of thickening it out more and more, and you wait till they overlap each other. There's sort of other characterizations in terms of the distance from a point to a set, but this is a nice one. And this is a fine metric, but it does have the issue that if you think about here's R2, that's X. And now I think about this circle and this circle. I'd like those to be close, maybe. I don't really maybe care that those circles came to me embedded in different places in R2. I mean, maybe I do, but let's imagine that you could imagine caring about that. But a lot of times, especially again, given motivated by the needs of data analysis, you don't, because the embedding is not some thing about your data. It's usually something about how you're measuring stuff. And so the Hausdorff distance would say these are quite far apart, right? Because if I'm start to thicken out this circle and thicken out this other circle, it's going to take quite a long time before those thickenings overlap, right? If I start to take the epsilon neighborhood of this thing, I'm spending a lot, it keeps getting bigger, and eventually it does envelop the other one, but it takes a while. So the idea of the Gromov-Hausdorff distance is, well, you just take the inf for any two metric spaces, you look at all possible embeddings in some bigger ambient space, isometric embeddings, and you take the inf of the Hausdorff distance. So in the case of these two circles, well, there's this embedding, but there's also the embedding that puts them on top of each other. And for that one, the Hausdorff distance is going to be small. And that's the metric. Now, this is conceptually very appealing. And for instance, it's now obvious that this is, this is invariant to all sorts of transformations, as long as you change by an isometry. It is also, it looks in principle uncomputable. But one thing that's nice is that for finite metric, you can define this for infinite things, but for finite metric spaces, you can compute this again in terms of a matching problem, where, let's go back to a different color. You can compute this in terms of a matching problem where you're minimizing some kind of distortion penalty, which looks at, if you take 2 points, what was their distance originally, and what is their distance? You match all the points of the spaces, and then you ask, what's the discrepancy between the points originally and their matched counterparts? It is not 100% obvious that this is the same thing, but it is true. So, okay, so now we're in a situation which is really quite different in flavor from what happens. So what happens traditionally is in homology is I have a space and I get a vector space, or I get a family of vector spaces, one for each natural number. And that's supposed to summarize something about the topological structure of the space. Here, I have a finite metric space, and for each finite metric space, I get a barcode, and the set of finite metric spaces is a metric space. The set of barcodes is a metric space. And this leads to sort of what I would argue is kind of the most basic and important result in the subject once you've set up the definitions, which is called the stability theorem. And this is the original version of this is due to Cohen, Steiner, Chazal, and Harrer. And what this says is it says that the barcode, the distance between the barcodes, so I guess I'm now introducing this notation in the theorem, but PHI and X is the barcode for X for I-dimensional homology, and similarly for Y, that the bottleneck distance, this matching distance between those barcodes, is bounded by the Gromov-Hausdorff distance between the original metric spaces. So this is a great result, right? Because this tells you that if you perturb your data in the Gromov-Hausdorff distance, then, what happens? You perturb your homological output just by a little bit. And that tells you, right? This is a sanity check. So you're not going to compute this stuff, but this is you should think of this as being something like an asymptotic result in statistics. If you didn't have this, you'd be screwed, right? It's just a disaster. Now I should also say that what this protects you against is perturbations that are small in the Gromov-Hausdorff distance. And if you think about the Gromov-Hausdorff distance, so if your model of noise is every point gets pushed a little bit, or I take some extra samples that are concentrated on my real data, then this tells you you're in good shape. If your model of noise is a malevolent demon adds a very complicated, low measure, tiny topological object far away from your signal, this isn't going to help you. And so there's a whole other theory, which I'll say nothing about today, but I want to flag as something interesting about thinking about questions of robustness, having to do with what I think Shmuel Weinberger likes to call, handle bodies at infinity. But because you can add if you add very complicated little things that really you should think of as noise, they can change the persistent homology or the homology arbitrarily. Okay, so now let me come back to the question that I started with, which I think is an interesting one, which is that, we as modern people characterize homology in terms of the Eilenberg-Steenrod axioms. And they characterize this amongst functors or families of n-indexed functors by the following list of axioms. Number one, this is a homotopy functor. So that means that it preserves it takes homotopy equivalences to isomorphism, to factors through the homotopy category of spaces. Number two, there's an operation called suspension, which is if you have your space, if you take your space X and let's say X looks like this, and you draw cones on it, and you sort of glue them together in the middle, that something like that that construction ends up shifting. This is some proxy for crossing with a circle and keeping track of base point information. And that this shifts the index of your homology group. And then there are two other axioms that say that this stuff is computable. So the first one says that it factors through the homotopy category. The second one says that it's stable in a certain sense. And the next two say that it's computable because they allow induction. One of them says that if you have I wrote this as a cofibration, but if you have a closed inclusion, it's the way to think of this, a nice closed inclusion, then there's an exact sequence in fact, a long exact sequence of homology groups. So this lets you, if you built your space up by pieces that you include into each other, you can understand X by understanding sort of the quotient and the piece. Yes, this is an induction strategy, and a variant of the induction strategy says that if you take the union of things, that what you get is the sum. And this basically characterizes it. I guess I am writing this slightly imprecisely or incorrectly, because you also have to stipulate that what the value is at a point. But once you do that, that characterizes this. And so the question that I want to ask is, or I want to put to you as an interesting one, is what is the right analog of this kind of axiomatic characterization as a collection of functors for persistent homology? And this raises, like, immediately we are confronted with difficulties because, so I wrote this as a homotopy functor, and so that means it preserves weak equivalences, preserves homotopy equivalences between nice spaces. What should an approximate weak equivalence be? That's probably what we want, some notion of approximate weak equivalence, because we have this metric all of a sudden. But what does an epsilon weak equivalence mean? Like, what should you mean by that? So in general, like, what is a weak equivalence in the context of persistent homology? And even that question turns out to have like an interesting and subtle answer. And I think that there's a reasonable answer at least to that question. But even if you answer that, what do any of the rest of these things mean? And really, we don't know. But let me start to tell you some things that we do know to sort of frame at least a little bit about how to think about this. So what happens is that, I stated the stability result, and the stability result, the original, I stated it as a metric thing, but there's an algebraic version of this, which is effectively categorical. And it is defined in terms of a notion of interleaving or diagrammatic. And so, if you have, let's think if we just have a functor x from R with its order to top, then I guess positive reals to top, then for any real number, I can define a delta shift by translating by delta before I evaluate. And so I can shift these things up and down and translate them. And so our definition is that an epsilon interleaving between two functors, x and y, of this form is a collection of a pair of maps, or really a family of maps, from x to the epsilon shift of y and y to the epsilon shift of x, such that both composites, right, if I go from x to y epsilon to x2 epsilon, that's just the translation up along, that's just the structure maps of x. So what this looks like, if you haven't seen this before, this is maybe hard to assimilate from that formula. Well, what the picture of this looks like is something like this. You have a ladder, right? And what I'm asking is that if I go up by epsilon and then back over by epsilon, that's the same as just going along in the filtration of x. And this is called an interleaving. And if you have an interleaving, you can define, once you have the notion of an interleaving, you can define the interleaving distance between two functors. And the interleaving distance between two functors, well, it's the minimum epsilon such that there exists an interleaving. And it turns out that you can relate the notion of interleaving to the Gromov-Hausdorff distance and to the bottleneck distance of barcodes. And so that you can think of the proof of the stability theorem as going through really a result about the behavior of the interleaving distance. So this gives us a way now, it turns out, to think about the notion of approximate weak equivalence or approximate homotopy equivalence, where this notion is strict, right? I'm asking for this diagram to actually commute. But really, it turns, if you are a homotopically minded person, what you might think is that we should ask for this diagram to be homotopy coherent or something like that. You could ask for this diagram in the homotopy category of spaces. That's wrong for the reasons it always is. But you could ask for it to be homotopy coherent. And indeed, that is the right thing to say. So I think that the definition I would put forward is that an approximate weak equivalence should be thought of as an epsilon homotopy interleaving. And you could think of that as the existence of a homotopy coherent epsilon interleaving. Or you could think of that as I'm allowed to replace x by x prime, which is weakly equivalent to it, and I'm allowed to replace y by y prime, which is as a functor is naturally weakly equivalent. So I have a natural transformation through weak equivalences between x and x prime and y prime. And now I have a strict interleaving between x prime and y prime. And the theory, essentially the theory of model categories tells us that that's the same as thinking about homotopy coherent diagrams. So you can talk about it however you want. And moreover, for something like, this is pretty general for the category of spaces. In fact, here we could define this in terms of arbitrary zigzags. But for the category of spaces, we know we can think about short zigzags, right? The calculus of fractions type arguments tell us that we only need little zigzags to actually control all of this. So now it's not trivial. It is true, but it is not trivial to prove that this is a metric. Because you're asking a question, if I have, a homotopy coherent diagram like this and a homotopy coherent diagram like that, and I put them together, can I produce from them some homotopy coherent diagram like this? And so there's some kind of algebraic question about, homotopical question about gluing homotopy coherent diagrams. And it turns out the answer is yes, but that takes a little bit of work. And then the next theorem about this you show, and what I'm describing in this part is work that I did with Mike Lesnick, who is one of the people who's done sort of lots of work on the idea of the interleaving distance and this algebraic stability. And what we show is that this metric, of course, there are many metrics you could put on things, but what we show is that this metric is universal. Universal for the following properties: that it has a stability theorem, it is homotopy invariant, and it's maximal in that it does the most separation. So any other metric that has those first two properties is smaller than the metric you get out of homotopy interleavings. And so I would argue that this is a sensible notion of approximate weak equivalence. And for the base, and it is true that persistent homology, the stability theorem tells us is sort of the equivalent now of the first axiom, namely that's our version in the persistent setting of what it means to be homotopy invariant. Okay, and so now if we have a good notion of approximate weak equivalence, and actually I should say for a second, one thing we know, and I have been sloppy about moving between these in this talk, but one thing to say is that in topology, there's a relationship between homotopy equivalence and weak equivalence. And what weak equivalence means is induces an isomorphism on homotopy groups. Homotopy equivalence means you have a pair of maps that are, that behave like an isomorphism up to homotopy. And one might wonder, is there some kind of notion of homotopy group by which I can characterize these approximate weak equivalences? And and we don't know. It's a reasonable question to ask. Moreover, what about, you can very reasonably ask, what about the rest of the axioms? And one kind of question is that the right question to be asking? Maybe the Eilenberg-Steenrod axioms are wrong and you should have a different set of axioms. Maybe, if not, and it's not clear, we don't know what the right axioms are. One version of refining this is that a big part of the Eilenberg-Steenrod axioms is this notion of stability, that if you shift by suspending, or you take loops on something, that moves your groups up and down. And that's, we have no idea what that should mean in the context of persistent stuff. And this is related, there's sort of one of the questions really that maybe you're asking is, what is the persistent stable category? Is there a category of persistent cohomology theories, and are there persistent spectra or some kind of representing objects that control these? And again, we don't have good answers. And a last question of this forum is what should mapping spaces look like? One of the big ideas, really that sort of is, in some sense, goes back a long way in algebraic topology, but in the abstract context was really intensively studied by Dwyer-Kan, and is certainly at the core of modern work on infinity categories, is that you want to think about your topology and your homotopy theory as encoded in mapping spaces. If you know what a topologized set of maps between objects is, then you know how to talk about homotopies. Because a homotopy is just a path in the mapping space, right? So if you have that, so what does that mean here? And that's closely related to homotopy groups. And to give you an example of the kinds of issues that arise, and I'm going to conclude by just sort of highlighting a little bit about why this is interesting and subtle. Let's imagine we have our combinatorial notion, maybe I want a red pen, of space. So I'm gluing spaces together from points and lines. And here I have a map from, a model of a circle to a model of a circle. But if I require, and this thing, these things really are, if you think about the spaces associated to them, they really are homotopy equivalent to circles. But if I think about the maps, it's more subtle, because if I want to require, and this is sensible, that vertices go to vertices, then there aren't very many maps from this thing. There aren't very many maps from this thing to this thing. If I take this vertex to this vertex, well, I have to take this vertex to this vertex if I'm going to keep that line connected. And I have to take this vertex to this vertex. And so there's the map that goes around, and that has winding number 1. If I wanted other kinds of maps that wrapped around the circle, right? For every integer, there's a homotopy class of maps that wraps around it that many times. I need to take a bigger model of my domain. I can add more points. And now if I do this, all of a sudden, things can be better, because I can wrap around this thing a couple of times as I walk around this hexagon-like object. There's now a feature scale for the mapping spaces. It's controlled by how much I've subdivided my model of my domain. And the finer I subdivide that, the more pieces I put into it, the more I can see in terms of the mapping space. And this is a manifestation of what's called the simplicial subdivision theorem, which says that you need to take smaller and smaller triangles in the domain to capture all homotopy classes. And so this gives an interesting connection to what's called quantitative homotopy theory. And what quantitative homotopy theory is about is, can you keep track of the length of homotopies when you do stuff? Can you filter homotopy groups by some sort of Lipschitz condition? And there's been this is a rich and interesting subject, that lots of people work on. Notably, there's been sort of spectacular work recently by Shmuel Weinberger and Steve Ferry and Fedor Manin and people around them. And so this is very closely related to some work of Larry Guth. I mean, there's sort of lots of different angles on thinking about this. In the topological context, in work, I just say something brief. I did some work with Mike Mandel to think, or not topological context, but topological data analysis context. You can look at some kind of what we call the contiguity complex, which is some sort of combinatorial model of a persistent mapping space, where you explicitly keep track of filtrations coming from this kind of subdivision. Now, but immediately, we don't know if how that's related to the notion of approximate weak equivalence I was describing. So what I would say is that there are, a topological data analysis has been around now for a little while, and there's lots of things we understand about it. But they're from a sort of an abstract homotopy theory perspective, or this perspective of categorizing these functors, we really don't understand it very well at all. And there's lots of interesting work to do. Okay, and that is a great place for me, I think, to stop the talk. So,
brilliant, thank you so much. People can unmute themselves to clap if they want, or use a clap emoji, because we live in the future. That was a very lovely talk, thanks. So feel free to kind of ask questions in the chat. I can read them out or unmute themselves. If you put up your hands, that would maybe be nice. We can do them in order. I see David's put his hand up, but I'm going to jump in first with my question because my hand was up in my head, so that counts. So one question, I guess I have a few, but I'll ask this one because it's the most recent thing you talked about, is this picture here where you look at kind of a triangle to a triangle versus like a hexagon to a triangle or whatever. So if you work with, say, like Vietoris-Rips complexes, like you say, these things are generated by their one skeleton, or like defined by their one skeleton. So you can just look at graphs. So can you get an interesting notion? So I know for graphs, there's this notion of a homotopy instead of homotopy, which is kind of like a version. So can you study like Vietoris-Rips complexes as like under this a homotopy equivalence and see what that gives you in terms of persistent homology?
That's a great question. I don't know about that, so I don't know.
Oh, okay, fine. Thanks for the answer anyway.
Yeah.
Okay, David, you had your hand up next. Would you like to go?
Okay, well, thanks again, Andrew. I guess my imagination is not so good. So can you give me an example? I can see if you have a map between spaces that it wouldn't factor, this homology obviously wouldn't factor through pointed sets. But for a given set, topological space X, or sorry, finite metric space X, where you just keep doing the Vietoris-Rips, can you tell me an example where it wouldn't factor through pointed sets?
Sorry, what's supposed to factor?
The Vietoris-Rips, the homology of the Vietoris-Rips. So I take my space, I turn it into a filtered simplicial complex, and I turn it into a filtered vector space. Could I have instead taken my finite metric space and watched the generators only of that thing, and seen when the generators go to 0 or when they go to each other, and just monitored that? In other words, factored through finite pointed sets.
You don't. I don't think so, right? Because generators could go to sums of generators, right? The algebra. You need the
in one of these inclusions.
I think so. You need the you need the algebraic structure in order to. What to say? Once you've gone to this barcode picture, of course, right? As you that definitely looks like something you could have gotten by thinking about finite sets. But I think that in order to actually get there, you need to be able to take sums of generators, because some of these things you're not going to be able to pick generators at every level for which that works.
Okay, so if you took the total functor, okay, so when you go to barcodes, you could have just factored through, because that's what a barcode certainly looks like. I'm factoring through through pointed sets. Is there a reason? And I guess the reason not to do that directly is that is there a reason not to do it directly? Is it because of maps between spaces that we're going to be worried about, or why not just go? Yeah.
Well, also because I think that you need to compute this as a matter of linear algebra, and
okay. And we have better ways of doing that than set theoretically.
Yeah.
Okay. All right. Okay. Thanks.
Okay. And Andreas, would you like to ask next?
Okay. I have a sort of a basic question. I had two thoughts while I was listening to you, and thoughts contradict each other, and I'd like to resolve this. So when you were talking about the Eilenberg-Steenrod axioms, the exactness axiom, you mentioned the long exact sequence in what you said, but in what was on the slide, there was only the part referring to one specific dimension with no connecting homomorphism. So my first thought was, oh, he just forgot to put connecting homomorphisms in there. My second thought was, no, he probably doesn't need them, because you've got the suspension axiom, and that should take care of connecting things. Maybe that together with homotopy and embedding things in cones and so on. So the question is the existence and naturality of the connecting homomorphism supposed to be part of the exactness axiom?
Yeah, it is. I was being sloppy. I'm sorry.
That's a shame, because I really was hoping that it would just be redundant.
Hello. I'm wondering if you or somebody else could share a pointer to how your description of the Eilenberg axioms, your description of them correspond to Eilenberg and Steenrod's original description.
Right.
In which there's no mention of exactness
right.
Following from a fibration,
right? Which uses excision, for instance, I think. So yes. So what I would say is, I mean, there are probably lots of treatments, but I was a Peter May student, so I would recommend Peter May's book, A Concise Course in Algebraic Topology, where he writes out many different versions of the Eilenberg-Steenrod
great, excellent. Thank you.
And talks in a nice way about how they're related.
Beautiful, thanks.
Yeah. And it's available to PDF online also. So.
I was referred to it when I studied that subject, but I barely used it as I was studying other things. Okay, thanks.
Yeah.
Okay, Andreas, do you have another question? Or
Oh, I just forgot to put my hand down.
That's okay. Sorry, don't worry. Okay, does anybody else have any questions? If not, I might permit myself to ask one more. Okay, so here's another question, which is kind of, if we're looking, like you have this really nice goal of like, you want to just study like Eilenberg-Steenrod axioms, approach to homology. So what happens if you don't take homology in finite fields? So you end up working with modules instead of vector spaces. Like, I remember when I studied this stuff, I was like, you probably can't do anything because, you know, you don't always have generators, and but the fact you use the art in Rieslemmer at some point makes me think, you know, there's some good commutative algebra going on here. So like, what can you say about this kind of case?
Yeah, so you're not in good shape. And the reason is because the theory of barcodes, the existence of these barcode pictures depends on knowing that there's a structure theorem for modules over polynomial rings. And well, we know that for FP adjoin T. And for Z adjoin T, it's a disaster, right? There's no structure. There's no good structure theory, right? Where's the barcode coming from? What it's really saying is that any module over R adjoin T is a bunch of free parts, which are infinite length bars, and a bunch of parts that look like, you know, Z adjoin T mod T to the N. And that N is the length of the bar. And so that structure theorem is what tells you this. And if you don't have that structure theorem, then you can't play this game. I mean, you get something, right? There's some kind of algebraic invariant, but it doesn't have a nice picture. It doesn't necessarily have a nice metric, and you have to work a lot harder to deal with it. Now, people study that stuff because there's interest in what's called multidimensional persistence, where, you know, one direction is the feature scale, and another direction is the feature scale, and another direction is density, let's say, or, you know, or if you're looking at an image, maybe it's intensity of the image or something like that, right? There's lots of natural situations like that, and the and in that case, it's you know, what you get. There's no for modules over even FP adjoin XY. There's not a good structure theory, and so it's much harder. But it's been studied a great deal, but there's no nice invariants like this, and so that's what happens. So you could do it, but there's a lot of focus on FP because of structure theory.
Okay, that makes sense. Thank you.
Yeah.
Okay. Does anybody else have any questions? No. Okay. In that case,
well, I have one little question. You mentioned the Artin-Ries lemma.
Yes.
In linear algebra. I'm wondering, does it merely mean in linear algebra that if U is a subspace of V, then there is a basis for V that has a subbasis for U contained in it?
Maybe. With the version that the result that I really want is the correspondence between filtered R modules and R adjoin T modules. And then you can choose a basis for the R adjoin T module, which gives you a compatible basis all the way through.
Okay. Right. Thanks.
Okay, we've just got one question from actually the YouTube live stream here, so I'll just read that one out quickly. So it says, I'm guessing that something like Kantorovich duality from optimal transport. That's all the question says. I don't know if you have any responses.
Kantorovich duality from optimal. Sorry, I lost. I think you muted the middle.
Sorry. I did accidentally click mute when I switched windows. It says, I'm guessing that something like Kantorovich duality from optimal transport theory works here.
since I don't remember what Kantorovich duality is, I can't comment. Optimal transport theory is there are ways in which optimal transport theory is of course very relevant to thinking about discrete geometry, but I don't remember what Kantorovich duality is. So
that's okay. I might have missed when this question was asked, and it was probably more relevant at the time. So that's my fault. But thank you again. So if we would all like to thank the speaker again.
Question later. Are we going to stay on for a while?
I was just about to say yes.
I have to go, unfortunately, but
that's fine.
But
okay.
I apologize. But if you have questions, please feel free to email me or
Okay.
Get in touch.
That's okay. Thank you very much again, Andrew. I will leave this room open anyway then, but obviously please feel free to go. That's fine. Thank you all, and I will see you all next week. Thanks.